In this video, we're going to practice calculations for a weak base strong acid titration when you are past the equivalence point. I can tell that we're past the equivalence point in this problem because the number of moles of my acid that we're adding is greater than the number of moles of weak base that I started with. To show you what I can see, we'll set up our regular fake rice table with the reaction that we're doing with our weak base and our strong acid. Now I'm writing this guy without the chlorine in there so that we can have a net ionic equation. And all we need to do to find our moles is take these milliliters and change them into liters and multiply it times the molarity. In this case, because our molarity is a convenient number, we just have to move over the decimal place. And I'll do the same thing for the hydrochloric acid. Now what's going to happen here is that our weak base is now our limiting reactant instead of our strong acid. So we'll subtract away the number of moles equal to the weak base, which leaves us with none of our ammonia left, and 0.0012 moles of our H plus left over, and 0.0025 of our weak acid, or rather the conjugate acid of our weak base. Okay, now before I can take these things and put them into a fake rice table, I generally will take these moles that we have in our fake rice table and divide them by the total liters. Today we have 25 plus 37 milliliters, which gets us 62 milliliters total inside of our container. So I'm going to divide both of these numbers by 0.062 liters, which means that my hydrogen ion concentration will be 0.0194. I'll just keep one extra sig fig, and 0.0025 divided by 0.062, 0.040 molarity for our ammonium ion. Now that we know that we have significant quantities of our H plus and our NH4 plus, we need to figure out how to most effectively find the pH. Because I don't have any more of my ammonia, NH3, in my solution, I now have the case where the ammonium ion will once in a while donate its extra proton to water to form ammonia and the hydronium ion. For our calculation purposes, the hydronium ion is the same thing as the H plus that I wrote in my last equation. Okay, so let's go ahead and fill out our rice table and then see if there's anything else that we need. All right then, our NH4 plus concentration that we had before was 0.040, and our ammonia was all gone, and our hydronium ion, or our H plus, is starting at 0.0194. Okay, now if we continue to fill out this rice table, which we totally can, if you really want to, we could get ready to shove all of this inside of a nifty Ka expression. which in this case would have ammonia and hydronium ion on the top and the ammonium ion on the bottom. And then we could, if we wanted to, find this Ka using Kw equals Ka times Kb, or you could look up the Ka in a book, but honestly, that's a lot of work. If we look at what our x value actually is, and the fact that the Ka for this scenario is 5.6 times 10 to the negative 10, which is a really small number in comparison to these starting concentrations, we would generally use the 5% rule and just cross off these x's. Finding x for this type of problem is not really helpful. Our ammonia is not going to be directly affecting our pH, not like the hydronium ion does, considering it's part of the definition of pH. So all I need to do is just take this concentration of the H plus that I already know and put it inside of a negative log. So I'll do that really quick in my calculator. I'm going to be using a stored number, so the number I get might be a little different than yours. And I'll just write down pH equals 1.713. That's probably too many sig figs. We've got 2 sig figs in this starting, so I'll stop it at 1.71. Now you'll notice that we're ending in such a low pH, and that seems a little weird at first after you've done a whole bunch of weak acid strong base titrations. But if you think about it, we started with a weak base and we kept adding more and more and more H pluses, so ending at a low pH makes a lot of sense.